Welcome to Lecture 7, Part 1 on groundwater hydraulics. We will continue with one-dimensional groundwater flow cases in the x direction. For the following case, steady groundwater flow in a leaky, homogeneous isotropic aquifer, we will also deal with seepage, steady groundwater flow through an overlying leaky confining or semi-permeable layer, thus steady groundwater flow in the Z direction. This figure shows Het Hollands Profiel, a cross-section profile for the Dutch provinces of Holland, which is a special case or example of steady groundwater flow in a leaky aquifer. The figure shows a Dutch polder made up of a leaky confining layer consisting of Holocene clay overlying a leaky aquifer with Pleistocene sand. Water is pumped from the polder and the hydraulic head or water table in the leaky confining layer is, to keep our feet dry, artificially maintained at the level HA in meter. In reality, this HA would lie slightly below the land surface, but here, simply for ease of calculation, HA has been set at the land surface. As a reference level, a hydraulic head of 0, we will use the top of the underlying impermeable base. The dike in the cross-section is simplified to an impermeable vertical screen above the leaky aquifer. Water from the river flows horizontally into the aquifer, and part of the water seeps upward through the confining layer, where again, to keep our feet dry, it is pumped off into the river again. Because of this, both the volume flux through the aquifer and the hydraulic head in the aquifer diminish from left to right. The hydraulic head in the aquifer is given by this dashed line and can be measured by lowering a piezometer tube through the confining layer into the aquifer and then having the piezometer screen within the aquifer. The difference in the hydraulic head of the aquifer and the artificially maintained constant hydraulic head HA in the polder therefore also diminishes from left to right. In this example of Het Hollands Profiel, the right boundary condition is taken at infinity. At infinity, the horizontal groundwater flow through the aquifer has diminished to 0, and the difference in hydraulic head between the aquifer, the dashed line, and the polder, HA, has also diminished to 0, and thus the upward seepage through the confining layer also is 0. We call this setup of Het Hollands Profiel an infinite polder. For both finite and infinite polders, a finite polder being a polder with a fixed boundary condition to the right, we will see an example of this slightly later on, the hydraulic head distribution with horizontal distance x in the aquifer, thus the potentiometric surface shown as a dashed line in this figure, can be determined from the water balance of this column, or rather rectangle of the subsurface, and then described as explained in full detail in section M3 of my book by the following equation. H is the hydraulic head in the aquifer at location x in meter. HA is the artificially maintained hydraulic head in the confining semi-permeable layer in meter. E is the base of the natural logarithm, a mathematical constant approximately equal to 2.71828, etc. X is the distance from x is 0, and lambda is the leakage factor. In Dutch we call this de spreidingslengte in meter, and lambda is the square root of kd times c. Kd is the transmissivity or kd-waarde of the aquifer, and C is the hydraulic resistance or vertical flow resistance in the overlying confining layer. C equals the thickness or depth of the homogeneously taken confining layer, small d, divided by the vertical hydraulic conductivity, small k, thus meters divided by meters per day, giving days. So C is the resistance of the confining layer in days, and Kd describes the aquifer in square meter per day. Thus Kd times C is in square meter. Taking the root of this, we have the leakage factor, or in Dutch spreidingslengte, in meters. The leakage factor is large when the aquifer has a high transmissivity, or kd-waarde, and when the hydraulic resistance C of the confining layer is also large. Horizontal groundwater flow through the aquifer then dominates over the vertical seepage through the leaky confining layer, and as a consequence, in this Hollandse profiel, the hydraulic head in the aquifer, H, then diminishes relatively slowly with distance x from the left canal. Conversely, the leakage factor is small when the leaky aquifer has a low transmissivity, so a low Kd value, and when the hydraulic resistance C of the confining layer is small. Vertical seepage through the leaky confining layer then dominates over the horizontal groundwater flow through the aquifer, and then as a consequence in this Hollandse profiel, the hydraulic head in the aquifer then decreases relatively fast with distance x from the left canal. The main equations in determining the shape of the potentiometric surface of the aquifer are, as to be expected, the continuity or water balance equation and Darcy's law, the Darcy equation. In section M3 of my book, these are combined for this column or rectangle. I will now only highlight the ingredients, so to speak, as some of these will be most useful when making hydrological calculations for leaky aquifers. This slide shows that column again. Here we have the aquifer with depth large or uppercase D, horizontal hydraulic conductivity large K, width W, and horizontal distance delta X. And here we have the confining semi-permeable layer with depth small or lowercase d, vertical hydraulic conductivity small K, and the artificially maintained hydraulic head HA is given here, is drawn in as a flat plane. And here below we have the confining layer again, but now turned on its side. The water balance for the aquifer part of this rectangle of the subsurface, using units of square meter per day, reads the volume flux Q in the x direction equals the volume flux Q out in the x direction plus the volume flux Q out in the z direction. The volume flux Q in the x direction square meter per day equals the volume flux density Qx in the x direction meter per day times the depth d perpendicular to the groundwater flow, the depth d of the aquifer. The volume flux density Q out in the x direction also equals the volume flux density times the depth of the aquifer, but now with regards to the volume flux density of the groundwater flowing out of the rectangle. dqx dx is the rate in which qx changes with x. Merely as an example elucidating this principle, the slope in this small figure. By multiplying this rate of change, this slope, with the section delta x where the change takes place, we obtain the total change dqx dx times delta x over the section, as indicated along the vertical axis here. Q out in the x direction can then be represented by this equation. Darcy's law for the aquifer can simply be written as Q with a prime in the x direction equals minus the Kd of the aquifer times the hydraulic gradient. The hydraulic gradient is the slope of a tangent line touching the potentiometric surface, the earlier dashed line, at a chosen location x. In this Holland's profile, the hydraulic gradient diminishes to the right. For the vertical volume flux density in the confining layer, we can write Qz in meter per day equals minus K, the vertical hydraulic conductivity K, times the hydraulic gradient. The hydraulic gradient is the hydraulic head to which the water flows, thus HA, minus the hydraulic head from where the water flow dispatches, H of the aquifer, and this hydraulic head difference we must then divide by the location to which the water flows minus the location from where the water flow dispatches, thus the thickness or depth small d of the confining layer, d for upward flow being a positive number. And then, of course, the volume flux in the z direction equals the volume flux density in the z direction times delta x perpendicular to this vertical flow. Inserting all these equations in the above continuity or water balance equation and some smart mathematics, again, for those interested, study section M3 for full details, delivers the hydraulic head distribution of the aquifer with horizontal distance x as this equation, with lambda being the square root of Kd times C. So now we have a third equation for table 3.3 to add. Again, the values for the constants C1 and C2 can be found by inserting the boundary conditions. For a finite polder, as shown here, the boundary conditions with both a fixed left boundary and fixed right boundary are: when x is 0, h equals h0, and then h0 equals ha plus c1 e to the power 0 plus c2 e to the power 0. E to the power 0 is 1, so h0 equals ha plus c1 plus c2, and thus c1 plus c2 equals h0 minus ha. When x is L, then h is HL, and HL equals HA plus C1 e to the power L divided by lambda plus C2 e to the power minus L divided by lambda. So all of this then equals HL minus HA. We have now two equations with two unknowns, C1 and C2, and we can solve that mathematically. For an infinite polder, het Holland's profile, as shown here, the boundary conditions are: when x is 0, then h equals h0, and then h0 equals ha plus c1 e to the power 0 plus c2 e to the power 0. So H0 equals HA plus C1 plus C2. Thus, C1 plus C2 equals H0 minus HA. When x is infinity, then H becomes HA, and then HA equals HA plus C1 e to the power infinity plus C2 e to the power minus infinity. Thus, C1 e to the power infinity plus C2 e to the power minus infinity equals HA minus HA, which is 0. So this term equals 0. Of course, e to the power minus infinity is 0, and e to the power infinity is infinity. And in order for this addition of terms to be 0, this term already is 0. C1 must be 0. So C1 is 0, and thus C2 equals H0 minus HA. We can insert C1 and C2, these values for C1 and C2, into the original equation. And then this is the equation we get, thus an equation without this term in it. If one wants to calculate the seepage volume flux into a polder in square meter per day, there are two routes one may take. In my book, there is a worked out example of determining the seepage volume flux for an infinite polder using both methods. Here I will discuss the steps to be taken for a finite polder. Please regard C1 and C2 as known values already obtained by having inserted the boundary conditions. The easiest solution probably is the horizontal solution. Recognize that as groundwater flow is steady or stationary, the vertical water seepage in square meter per day must be equal to the horizontal volume flux in square meter per day entering the leaky aquifer at axis 0 plus the horizontal volume flux in square meter per day entering the leaky aquifer at axis L. Here we have the Darcy equations for water entering at axis 0 and water entering at axis L. Please recognize that as water flow is to the left here, your answer will be negative. And if you want to know your total seepage into the polder, you have to add the absolute values, thus the positive values together. The hydraulic head is stated here. When you differentiate this, you get the hydraulic gradient. Insert 0 in this equation and you have the hydraulic gradient at axis 0. Insert for xl into this equation and you have the hydraulic gradient at axis L. And then again, add the absolute values together and you will find your total upward seepage into the polder in square meter per day. Your answer can be in minus lambda divided by C times this term, or minus KD divided by lambda also times this term. And these terms are related to each other, and you can see that here lambda is the square root of KDC, so lambda squared equals KDC. So this is the relationship between lambda divided by C and KD divided by lambda. Another solution would be the vertical solution. This is another way for determining the vertical upward seepage into a finite polder. You do this by stepping up from the volume flux density, small qz, in meter per day. This is the volume flux density through the confining layer, and you step up towards your volume flux, your upward seepage in square meter per day. And as you can see, this is done by mathematical integration. As you want to know the upward seepage for all of the polder, you must integrate between the bounds of 0 and L. You insert the Darcy equation into this integral equation. Of course, your Darcy equation, as its vertical flow, you write in this shape: the vertical volume flux density equals minus the vertical hydraulic conductivity, and then times the hydraulic gradient through the confining layer, which is the hydraulic head to which the water is flowing. So that's your artificially maintained level in the polder, minus the hydraulic head from which the water flow dispatches in your aquifer. So that's this H. And then you divide by the distance. And as water is flowing upward, this distance is a positive number. So you insert this into this equation, and this is what you get. And if you integrate between these two bounds and you insert for H this equation, or likewise for HA minus H, this equation that's doing the same thing, you will find this as an answer. And it's the same answer as we found by using the horizontal solution as it should be. When solving the upcoming leaky aquifer exercises, as mentioned earlier, always start off with the correct Laplacian equation as given in table 3.3. So that's this equation with C1 and C2 still to be determined. Analytical solutions to groundwater flow problems are especially useful as they provide a quick first estimate to many groundwater flow problems. But always be aware that in practice there may be complicating factors, as for instance is evident from this picture. A picture taken from the PhD thesis of one of our former Utrecht University students, Dr. Perry de Lauw, where a shallow rainwater lens overlies saline groundwater with a brackish mixing zone in between, and where also the saline groundwater is shown to be reaching the surface water by upward seepage along a preferential pathway. A problem, this upward seepage of saline groundwater, that may be further enhanced by future sea level rise, as this will cause an increase in this upward seepage into our polders. Preferential pathways for upward seepage are especially evident from this picture, also taken from the PhD thesis of Perry de Lauw, that shows different types of boils. In Dutch we call these vellen in deep polders. A pin boil, a sand boil where sand is transported upward with the water flow, a boil emitting naturally occurring methane, which is, as you are most probably aware, a most potent greenhouse gas in the Earth's atmosphere, thought to heavily contribute to the enhanced greenhouse effect, versterkte broeikaseffect. A sand pseudovolcano, a collapsed ditch bank, holes in the ice caused by warmer water welling up from a boil, sand boils on land, and here we have a schematic diagram of boils showing several subsurface conduits or preferential pathways. This picture shows steady groundwater flow in a recharged, unconfined aquifer bordered by two parallel, fully penetrating canals with equal water levels. The aquifer is homogeneous and isotropic, and the Dupuy-Forchheimer assumptions apply, same as with the steady unconfined groundwater flow that we discussed earlier. Again, we may combine Darcy's law for unconfined groundwater flow, taken as horizontal, as stated here, with the continuity equation for a recharge situation, Q with the prime equals n times x, where n is the recharge rate or precipitation surplus in meter per day, and x is the horizontal distance in meter. So both the horizontal Q with a prime and Nx are in square meter per day. As specified in section M4 at the end of my book, this delivers the following equation for the potentiometric surface. Please note that because the present flow case is symmetrical, the location of x is 0 is taken in the middle, where h as h0 is largest due to the recharge, and that groundwater flow is from the center of the aquifer in opposite directions to both canals. When h0, hl, and l are known values, C in this equation can be found by inserting the boundary conditions for this flow case. First insert the x is 0 mid-boundary condition and then the x is L boundary condition. Same as with the first derivation of the Dupuy-Forchheimer equation for unconfined groundwater flow in an earlier lecture, the horizontal length L of the aquifer must be at least 5 times larger than the saturated aquifer thickness D with a bar above it, which again we may take as H0 plus HL divided by 2. Define the convexity delta H as H0 minus HL and split H0 squared minus HL squared as shown here, and this will deliver this equation. This equation is a simplified version of the Hooghoudt equation, named after the Dutch hydrologist Simon Barend Hooghoudt. This equation, shown here again, can be rewritten as shown here. This equation gives the drain spacing 2L, so this distance between drains or between these two ditches, as a function of the recharge rate N in meter per day and the convexity delta H in meter for an aquifer with a transmissivity Kd in square meter per day. As the land surface in polders should not be too wet in order to still allow for farming practices, this restricts the values for the convexity delta H, it is a very useful equation to determine the optimal distance between ditches that drain these polders. Typically, take the train from Utrecht to Amsterdam or for another part of the Western Netherlands, and you can see the meadows to be quite evenly partitioned by these ditches. This figure shows steady groundwater flow in a recharged, unconfined aquifer bordered by two parallel, fully penetrating streams, but with different water levels, as for instance in mountainous areas. The aquifer is homogeneous and isotropic, and also here the horizontal length of the aquifer must be at least 5 times larger than the saturated aquifer thickness in order for the Dupuy-Forchheimer assumptions to apply. Again, and as specified in section M5 at the end of my book, we can set up the water balance, shown here, for a vertical column or rectangle of the aquifer. You can think of this area constituting that rectangle. And then combine this with Darcy's law. You see Darcy's law stated here on the top lines to obtain this equation. Note that also here we are dealing with an unconfined aquifer. H and dH dx are taken together as one term. N is again the recharge rate or precipitation surplus in meter per day. And also note that for n is 0, we obtain the earlier equation h squared equals C1x plus C2, the equation for an unconfined aquifer between two parallel, fully penetrating canals with different water levels, and, as we now may add, with no recharge. So in actual fact, the earlier equation h squared equals C1x plus C2 can be regarded as a special case of this new groundwater flow case. Note that as this flow case is not symmetrical, the location of axis 0 is now taken to the left. And we find values of C1 and C2 by inserting the boundary conditions as explained earlier. First insert the left boundary condition and then the right one, etc. Also remember that from work by Hachema and others, as mentioned in an earlier lecture, a low average annual recharge rate in comparison with the aquifer's transmissivity is favorable for the establishment of such a recharge-controlled water table. We can extend our starting point table 3.3 with the two-letter Laplacian equations, as shown here. As advice for making proper calculations, do not round off any of your in-between results, especially so for the C1 and C2 values of a leaky aquifer. As best practice, use symbols such as H0, HL, L, etc. instead of their known values in your calculations right up until the end. That is, insert their values at the end. Even better, make use of carefully built up spreadsheets for your calculations. Part 2 of this lecture will be on radial groundwater flow to or from wells.